Good afternoon, everyone. This is Advanced Thermodynamics and Combustion course being conducted by IIT Guwahati under the NPTEL program, that is National Program on Technology Enhanced Learning. And we are into the eighth live tutorial session of this course in this current academic session. And in this session, we will be starting with a new topic, that is combustion and thermochemistry. Before this, we dealt with different types of mixtures and the discussion around such mixtures. And the instructor for the course, as we all know, is Professor Niranjan Sahu. He is from Department of Mechanical Engineering, IIT Guwahati. And my name is Aditya Sharma. I'm a research scholar from Department of Mechanical Engineering, IIT Guwahati only. So we shall be starting the session in another couple of minutes. So till then, let's just wait and see if somebody joins. Otherwise, we'll start our session. Thank you. Okay, so let's start with the today's session. So the session has been divided into three sections. First is the topics that have been covered in the week 8 of this course. Then second section is on conceptual questions or theoretical questions, and the third section is on numerical questions. So we shall see these three sections, and at the end we will conclude the session in few 4 or 5 minutes. Okay. So in the last 4 or 5 minutes. So let's start with the session. So this uh, week is a bit lengthy in terms of the number of lectures and the content that is there in this week's lectures. So let's just start. So first lecture is lecture number 19. So as we have mentioned, the theme of this session is combustion and thermochemistry. So in that line, first topic here is combustion fundamentals. So here we will basically be dealing with combustion and the analysis around it. So we are basically trying to understand the combustion process. So various types of combustions that take place. So we will be dealing with all that in this. So in it, first subheading is reactants, products, and stoichiometric coefficient. So we can try to understand this. This this way. So this is combustion fundamentals. So we have our fuel, right, and then oxidizer, which gives rise to your combustion products. Okay, this is the basic framework, and we can take example of methane. So this is an example of combustion of methane. Take one such example. Okay. So here, this is your reactants. This is your products, and these are your stoichiometric coefficients. Coefficients. Okay. All right. Then is fuels and oxidizers. So in general, what we see is that the fuel we use has it's basically hydrocarbon. Okay, so it will have hydrogen. Also, it will have your carbon, right? So just I've written an example of methane, which is also a hydrocarbon. Okay, so this fuel will burn, and to burn the fuel or combust the fuel, we need oxidizing agent, right, or oxidizer. So oxygen in that case acts as an oxidizer, and which eventually leads to combustion of fuel. Okay, but when in reality, when we have to combust a particular fuel, what we do is that we don't give oxygen in its pure form, but we give air for combustion, right? So air is not just oxygen. Okay, in place of oxygen, we give air, but air is not purely oxygen. It will have nitrogen also. Okay, so for our analysis, combustion analysis purposes, what we do, we write air as in terms of moles. 1 mole of oxygen and 3.76 moles of nitrogen. So this is how we write our air. Okay. And then if I have to combust methane in the presence of air, okay, so it will be like this. We can balance it. Yes. So here it will be 2, here it will be 2 into 3.76. Okay. So this is how we will combust. We will write the balanced chemical equation when we are introducing air into the picture. So then is your stoichiometry. What is stoichiometry? Stoichiometry basically is the balancing of the elements of reactants with the products in a chemical reaction. This is basically stoichiometry, right? So in stoichiometry, we see a number of parameters like air fuel ratio, right? Then fuel air ratio, then theoretical amount of air. So all this we see in stoichiometry, right? And then what is a lean mixture, right? What is a uh, rich mixture, right? Uh, Lean and rich in terms of the fuel that is present in the in a mixture, right? So all this comes in your stoichiometry. Okay. Then is your equivalence ratio, which is also denoted by phi. So this phi basically is the air to fuel ratio at this to air to fuel ratio at actual. So in ideal case, when the fuel is neither rich in terms of fuel and neither it's lean, right? So this is an apt situation where the fuel will be totally combusted by the available your oxidizer. Okay, so that is your stoichiometric conditions or stoichiometric air to fuel ratio. But in actual, it's not always the case that the air and fuel in terms of their quantities are in the stoichiometric ratio. Okay, so in that case, air to fuel ratio can be different, and in that case we are writing here as AF of actual. Okay, so if your phi is less than 1, in that case we call it as a lean mixture. If phi is greater than 1, we call it rich mixture. And if phi is equals to 1, that is stoichiometric conditions. That is stoichiometric condition. Okay. So this is your equivalence ratio. Then there is a discussion on products of combustion. So it's a very brief discussion where we see that the different uh, products that we see after a chemical reaction. So if we have to analyze it, so how can we do it? So different devices have been mentioned, like offset analyzer and gas chromatograph, right? Right. All these have been mentioned in the lectures for analyzing the different products of combustion. Okay. Then is your next topic is thermodynamic properties of reacting system. So when we have a set of reactants, okay, so for those reactants, how do we define the enthalpy? Okay, so we when we have a fuel and air mixture, okay, for all these cases we consider that it is an ideal mixture. So in the last week, I believe we have done all the discussions on ideal gas mixture, right? So all that discussion is from this context only. So when we have to study combustion, so these mixtures, the study of these mixtures come into picture, right? So the same way here in reactants, we consider reactants to be ideal mixtures, and in that case, if we have to define their internal energy, their enthalpy, and their entropy, so all that how we can define. So all this has been discussed in this particular topic, right? So this was a basic on combustion, this lecture. Okay. Then next lecture is your lecture number 20. So here we deal with the reacting systems. Okay. So when we have to study reacting systems, so we need entropy data, we need enthalpy data, right? So how do we define all these, right? So in this discussion, we saw that if we want to have enthalpy of a particular element, okay, so what we do is we define the enthalpy in comparison to some standard reference state. And this standard reference state we define by taking some reference pressure and temperature. Okay. So for enthalpy, we take this reference pressure as 1 atmosphere and reference temperature as 298.15 Kelvin. Okay. That is 25 degrees Celsius. So in case of entropy also, this way we define a reference state. Okay. So this was your reacting systems. Then in your reacting systems, if a reaction is taking place and we get a set of products, right? In that case, if we want to find the enthalpy of formation of those products. So how do we do that? So this discussion has been done under this topic. Okay. Same way enthalpy will be defined using a reference state. Okay. And one important point to be noted is that when the reaction is exothermic, right? That means when there is release of heat during a reaction. In that case, the enthalpy of formation will be negative. Okay. And when the reaction is endothermic, that is energy is being absorbed by the reactants. In that case, your enthalpy of formation will be positive. Okay. So this is your enthalpy of formation. Then there is discussion on energy balances for your a closed system and then for your control volume. Okay. So control volume, you can take the system of a turbine of an aircraft, right? In that case, this energy balance for control volume can be taken, right? So in such a scenario, uh, how do we define our energy balance, or should we call it energy rate balance, right? Because we are dealing with a control volume, so the rate of energy is to be balanced. So the expressions for this have been given in your lecture slides. Okay. Yes. So for that you can refer to your lecture slides, and same is the case for your closed system, right? So all the expressions for it have been discussed in the lectures. Then is your enthalpy of combustion. Next topic is your enthalpy of combustion. So from the discussion in the lectures, we see that earlier we defined the enthalpy of formation, but what is the problem with this enthalpy of formation is that it doesn't give us realistic estimates for our systems, okay, reacting systems that we are studying. So in that case, what we do is we define this enthalpy of combustion, okay, which basically is the difference of the enthalpy of products and the enthalpy of reactants, right? When complete combustion of reactants has taken place, of a particular fuel has taken place, okay, in that case, the enthalpy of your products and the enthalpy of your reactants, the difference in that, this gives you your enthalpy of combustion, right? Later we shall see a numerical, very small, tiny numerical on this enthalpy of combustion. Okay, so this is your enthalpy of combustion. The last heading in this lecture is heating value of fuels. Right? So if you see the definition of heating value of fuels, it, so it says that it is the positive number equal to the magnitude of enthalpy of combustion. So this is basically the magnitude of enthalpy of combustion. This is your heating value. Then there are two types of heating values. One is high heating value and then other is low heating value. Okay. So what happens when we get reactants? With that we get H2O when we have a reaction, sorry, and there we get our products. So in those products, uh, one product is H2O also. Okay. So this low heating value and high heating value, this is defined based on the phase in which or state in which your H2O is. So it can your H2O can be in liquid phase or it can be in gaseous phase, right? So in case uh, your H2O is in liquid state, right? Your water is in condensed state. In that case, what we say is it's a high heating value, okay? And when your H2 or water is in vapor state, then we say that it's a low heating value of that, right? So because to convert your liquid into vapors, right? Some energy will be consumed, right? In that case, the energy, the heating value that will be in our hand when S2O is in vapor state, it will be less in comparison to the heating value when your water is in liquid state, right? Because the energy required for vaporization in this case is saved. Okay, so in that case we get a high heating value. So this is basically the difference between high heating value and low heating value. Okay. So this was your last heading in this lecture 20, and then is your lecture 21. So in the previous lecture, we saw there was discussion on energy balances for closed and closed systems and then control volume. Okay. Now here we will be seeing entropy balances. Okay, for both the cases, closed system and your control volume. Right. Then one important concept that has been introduced in this lecture is adiabatic flame temperature. So what is an adiabatic flame temperature? So when a combustion of a fuel takes place, right, we get some heat from that combustion. Right? So some heat is accompanied with the combustion products, while some heat is your dissipated in the surrounding. Okay, so these are the two elements of heat that we get from your combustion. But let's say we keep this combustion in adiabatic conditions and we do not let this heat dissipate into the surrounding. Okay, in that case, the temperature that your products will have or your flame will have, right, that we define as an adiabatic flame temperature, right? So this is the maximum temperature that can be attained by the combustion products for a particular fuel. So this is your adiabatic flame temperature. Okay. Then there are few inferences based on adiabatic flame temperature. Okay. So point to be noted is that adiabatic flame temperature can be calculated at two conditions. One can be when your volume remains constant, and one is when your pressure remains constant. And in the former case, it is seen that the adiabatic flame temperature is higher in comparison to the later case. Okay. So for constant volume case, your adiabatic flame temperature is higher in comparison to the constant pressure case. Right. Okay. So this is your adiabatic flame temperature. Then is your absolute entropy. So what is an absolute entropy? Absolute entropy is that entropy which is defined uh, with uh, a particular reference. Okay, and that reference is your entropy of a pure crystalline substance at zero temperature, absolute zero temperature or zero Kelvin. Okay, which is also zero, right? So this comes from your third law of thermodynamics. Okay, so entropy for a pure crystalline substance is zero at your absolute zero temperature. So this you take as your reference when you have to define the absolute entropy. Okay. So when the temperature increases, right, So in that case, what will be the entropy is defined based on this reference of 0 Kelvin. Okay. So this is basically your absolute entropy. Then your entropy balances are there. Okay. So entropy balances we have discussed a quite number of times now, right? So elements like entropy production, okay, that we uh, define using the symbol yes, this sigma, right? So discussion on this we have done. So all this now has to be done in terms of your reactants and your products. Okay. So all the expressions have been mentioned in the lectures for both your control volume at steady state and your closed system. Right? Then enthalpy production, uh, and then how the heat across the boundaries contribute to your entropy balance. Okay, so all this has been discussed in your lectures. Then your next topic is Gibbs function. So for these chemical reactions, how do we define the Gibbs function at a particular state? And then how do we define the change in this Gibbs function? Okay, so the expressions for it have been given in the lectures. All this discussion we have to keep in mind is keeping your combustion and your chemical reactions that take place during combustion in the mind. Okay, so in that case, how these mm, various discussions help in analyzing your combustion process. That perspective has to be kept in mind while studying this topic. Okay, so this is your Gibbs function. Then your next lecture is lecture number 22. In it, we see topics based on equilibrium. Okay, so when there is equilibrium between your reactants and products, so what is the situation in that case? Because there are cases where your whole uh, fuel will not combust. Okay, the case can be that the availability of oxidizer is not appropriate. Okay, in that case, we get uh, products other than the case in which a complete combustion has taken place. Right. So in that case, how the chemical equilibrium takes place and how do we study different products in that case. So from that perspective, discussion has been done in this topic, right? Then your next topic is equilibrium products of combustion. So when your both reactants and products are in equilibrium, in that case, what the situation is of the reaction. Okay, all this discussion has been done in this particular topic. So this is your topic, equilibrium. So if we have a lean mixture and if we have a rich mixture, in that case, so it says that these are your common products that you see. But in case it's a rich mixture, so what will happen in case of a rich mixture? The fuel will not combust totally, right? So some extra products you will get to see, right? For example, this carbon monoxide and hydrogen that you don't see in a lean mixture because total combustion of the fuel is taking place, right? So such type of discussions have been done in this equilibrium products of combustion. And then what the your equivalence ratio phi has the impact on the mole fraction of different products. So this has been shown by different graphs. Okay, for propane the discussion has been done. So how the equivalence ratio affects the mole fraction. So this has been done in this topic. Yes. Then next topic is your water gas equilibrium. Okay. So from your lecture, if you see, this is your slide number 15 of lecture number 22. So it says that for lean combustion only atom balances are done. And in case of rich combustion, a single equilibrium reaction is considered, known as water gas shift reaction. Okay. So this means that you'll have in rich mixtures combustion, you'll have your incomplete products in the form of carbon monoxide and your hydrogen. Okay. And how the this water and gas equilibrium is important in such a scenarios. So discussion has been done around this in this topic, right? For this water gas mixture. Sorry, water gas equilibrium. Then your next topic is recuperation and regeneration. So this basically is to increase the efficiency of your fuel that you are using. So in recuperation, what we do is that we have a heat exchanger, all right? So the heat uh, that we get from your combustion products, okay, basically the flue gases, the heat that we get from flue gases. So this is supplied to your air, okay. This is transferred to your air, that is that you are supplying for your combustion, right? So this way we try to enhance the efficiency of our fuel in the combustion process. So same is the regenerator. So a regenerator transfers the energy from your flue gases to your incoming combustion air. Okay. So this was a recuperation, and then we recirculate the flue gases. Okay, to enhance the efficiency of the your fuel or combustion of your fuel. So this flue gas recirculation is commonly seen in boilers, and then there is also exhaust gas recirculation, where the whole exhaust gas is recirculated. So this type is used in, yeah, automotive engines. Okay, so this is your discussion on flue gas circulation. All right. So these were the topics that were discussed in this week's lectures. Now we will move on to the conceptual questions. So let's see the questions one by one. So the first question is, number of moles in a combustion reaction remain conserved. So whether this is true or not. You can try to answer this. So the question asks that the number of moles remain conserved. So let's take this example. Now if you balance this, what you will get? this. Now if you see, this is 1 mole and this is 5. So total 6 moles are there, right? And if you see this and this, there are total 7 moles. Right? So the question doesn't ask that each element, the number of moles of each element, right? It just asks that whether the number of moles in reaction remain constant. So reading it this way, it comes out that number of moles, it's not always the case that they remain conserved, right? They do not remain conserved. For the different elements, though, it has to remain conserved, right? But the number of moles of reactants are equals to number of moles of products. This is not the case. Okay, that doesn't make sense. So this will be a false statement, right? So this was your question number 1. So moving on to question number 2. So this is your question on equivalence ratio. So you can try to answer this. So this is question on your equivalence ratio. For a lean mixture, what happens is that your fuel is less. Okay. So for your lean mixture, fuel actual is less than fuel stoichiometric. Stoichiometric. Okay. Right. In that case, when we say this as air to fuel of stoichiometric, air to fuel of actual, what will happen? Fuel is higher for which case? For same value of air, fuel is higher for stoichiometric, right? So in that case, implies less than, right? Which implies your phi is less than 1, right? So this will be your answer. The 4 options are given. C option is the correct one. There are options like phi is greater than equal to 1 and phi is less than equal to 1. So equal to 1 will only be there when the air and fuel are in stoichiometric ratios, right? Sorry. In all the other cases, it will be otherwise. Right? So C is the correct option. So moving on to your next question. This question is on enthalpy of formation. So we have discussed this in the topics. So this can be answered easily. Let's try to answer this. Okay. So in exothermic reactions, there is release of heat, and in endothermic reactions, there is absorption of heat. Okay. So for your release of heat, the enthalpy of formation is negative, and for your absorption of energy, this is positive. So this is a true statement. Okay. So see this. Answer is A. Right. So let's see now our next question of this section. So this is a fact-based question. This says that what is the reference pressure and temperature used to establish the enthalpy datum for reacting systems? Yes. So whether this is 1 bar, this, sorry. So whether your A option 1 bar and 0 degrees Celsius, 1 bar and 25 degrees Celsius, 1 atmosphere and 0 degrees Celsius, 1 atmosphere and 25 degrees Celsius. So we have seen in discussion that answer to this question is option number D. So this is your 1 atmosphere and 298.15 Kelvin. These are the reference pressure and temperatures using which your enthalpy is defined. Taking the enthalpy values at these pressure and temperature values. Okay, so D is the answer to this question. So we will take now a 5 minutes break because it's 4 p.m. already. So after 5 minutes, we shall start the remaining session. Thank you. Okay, so let's start with the remaining session. So this is question number 5. It says that the enthalpy of formation for stable elements at reference state is negative. Whether this is true or false. We can try to answer this. So the answer to this question is false. And why so? Because for your stable elements at reference state, this is basically zero. Okay. So if your statement says that it is negative, it's a wrong statement. So then moving on to question number 6, which is on heating value of fuels. So it says that the high heating value of a fuel is obtained when all the water formed by the combustion during the chemical reaction is in the form of dash. Options are liquid, gas, solid, either liquid or gas. So if we know how we define the high heating value of a fuel, we can easily answer this. Fill in the blank. So yes, please try to answer this question. Okay, so we have discussed that high heating value is defined when the water in your products is in liquid form, right? Because the if it was in vapor state, then some amount of heat of your combustion would be used in vaporization of that water. But when the water is in liquid state, it means that we have saved that energy, right? And in that case, we define that heat of combustion as heat from combustion as high heating value. Okay? So this will be liquid. Okay. A option will be the correct one. So this was your question number 6. Moving on to now next question. This is question number 7. So this says that this is on enthalpy of combustion. This says that the enthalpy of combustion is defined as the difference between the enthalpy of the products and the enthalpy of reactants when half of the combustion reaction is over at a given temperature and pressure. So whether this is correct or not. So this is a false statement. Why so? Because there is no such thing like half of the combustion. Okay. So enthalpy of combustion is only defined when your full combustion of the fuel has taken place. In that case, we define your enthalpy of combustion, and it remains this only, the difference between enthalpy of products and the enthalpy of reactants. But the combustion has to uh, take place fully. Okay, so this is your false statement. Now, next question is your based on absolute entropy. As per the third law of thermodynamics, the entropy of a pure crystalline substance is zero at absolute zero temperature. This is used as a reference to define the absolute entropy. So this is a true statement, right? This is a definition of your absolute entropy. We use this to define our absolute entropy. Okay. All right. So moving on to the next question. This is question number 9. We have four options, so we can try to answer this. So this question is from your adiabatic flame temperature topic. Okay. So the maximum heat transfer during a combustion process. It can be modeled only when uh, the combustion is taking place in adiabatic conditions. Okay. So to model that in adiabatic condition, and then in what type of reactor? The reactor has to be a steady state reactor. Okay. So this is from your lecture notes only. Not a reference state reactor, but a steady state reactor. There's nothing like a reference state reactor. Okay, so the option is correct. So this is from your adiabatic flame temperature topic. Okay, adiabatic flame temperature. Okay. Right. Okay. Okay, so I've shown the answer accidentally, but okay. We will still discuss this. So this is if a few layer mixture burns adiabatically at constant volume, the absolute enthalpy of the reactants at initial state is equal to the absolute enthalpy of products at final state. So whether this is the correct statement or not. So the answer is obviously B, but why B? So I was discussing earlier that two types of adiabatic flame temperatures are defined. One is at constant volume and one is at constant pressure, right? So in case of your constant this pressure, right? Absolute enthalpy of reactants and products is equal. But then for your constant volume process, the absolute internal energy is equal for reactants and products. Okay, so that is why B option is correct. Okay? All right. Though I have changed the animation sequence, but somehow still falsely came. Sorry for that. So here it also it will be internal energy, absolute internal energy. So next question, then which of the following is not a dissociation species? So yes, which of the following is not a dissociation species? So oxygen in this state, in its this free state, is a dissociation species. Nitrogen, single nitrogen, is also a dissociation species. Then oxygen O2 is not a dissociation species. This hydroxyl is also a dissociation species, right? So C option in that case is correct. Okay. So this was question number 11. Now moving on to question number 12. So this is on Gibbs function. So this Gibbs function attains a maximum in chemical equilibrium in contrast to minimum in entropy for a fixed energy and fixed volume case. So this is a false statement. Why so? Because for your chemical equilibrium, the Gibbs function is in its minimum state, okay, in its minimum value. And for your when we are trying to see chemical equilibrium in terms of your entropy, in that case it is in maximum, in its maximum value. Okay, so in that case this becomes a false statement. Yes. So we can try to balance it. This is question number 13 solution. This is what octane, which is C8H18 plus O2 plus 3.76 N2, which gives rise to CO2 plus H2O plus N2. Okay, now let's balance these. So, sorry, this is A, this is B, this is C, D, E. Now, 2B into 3.76 equals to 2E implies 3.76B equals to E, which is first. Then 8A equals to C implies not implies. Okay. Then third is hydrogen. 18A equals to 2B. Then your oxygen. What is oxygen? So oxygen says that 2B equals to 2C plus D. right? So A we have taken here as 1. So A, what will this become? C equals to 8. C will become 8. And this will become D equals to 9. D will become 9. C, D we have. So B we can find out. So this will become D equals to C plus D by 2. So D equals to C 8 plus 9 by 2. Right? Yes. So which is also 12.5, right? This D will become 12.5. This B is then 12.5. And what they have asked for C is 8, right? So D option will be correct. Okay, so D option is correct. So now we are done with the conceptual questions. Now we will move on to numerical questions. So this is the information given for question number 14 and 15. The fuel has been given in the form of propane and butane. And the air that we are using in, in comparison to the stoichiometric air is 115%, and fuels flow rate has been given as 25 kg per second. Okay. It should have been in terms of moles. Okay. Now Question number 14, let's see. It says that determine the required flow rate of air. So how can we solve this question? Please think on it. Okay, so let's solve this. So we have C3H8 propane and we have C4H10. So to combust these, we will require 3 plus 8 by 4 of O2, and for this we will require 4 plus 10 by 4 of O2. Okay. Using this information, we will solve this. Then also is given that this is 1.15. Okay. So first we will balance this equation. So this is C3H8 plus C4H10 plus. Now we will write for this oxygen and nitrogen. What is the coefficient of oxygen will be the coefficient of this whole bracket, okay? That will also be the coefficient of 3.76 of nitrogen, right? And the products that we have are carbon dioxide plus H2O, okay, plus oxygen plus nitrogen, okay. plus oxygen plus nitrogen. Now, based on the information given, we will write the coefficients. So this will be 0.6, this will be 0.4, and then 1.15 of your stoichiometric air is to be used, right? But what is the stoichiometric air? This is 0.6 of 3 plus 8 by 4. So this is for your uh, uh, the quantity, the value in curly bracket is for your propane. Then this is for your butane. Okay. Now the same way for your carbon dioxide. For water, then is for your oxygen, okay. So this is for your oxygen, and then for your nitrogen you have the same way 3.76 into 1.15, and then this one is for nitrogen. Okay. So now if you get, because you are concerned with the air fuel ratio, from your air fuel ratio, because you have been given for fuel the rate has been given. So if you once have you have the air fuel ratio, from there you can calculate the air's flow rate. Okay. So if you again write your reactants, so it will be 0.623H8 plus 0.4C4H10 plus. Now please calculate for oxygen how much the value will be. This should be around 6.44. And for nitrogen it should be 24.21. So please cross check this. Okay, so this is correct, I believe. Right. So now your air fuel ratio, actual air fuel ratio, this comes out to be 6.44 into 32 plus 24.21 into 28 and 6 into 44 for propane, 58 for butane. Please calculate for this also. Sorry. So this comes out to be 17.82. You may check the calculation, please. So then required flow rate will be equal to 25 into 17.82, and this comes out to be 445.5. So this is the answer. Then your next question is on what is the equivalence ratio of the mixture. So equivalence ratio, we have the percentage of theoretical air, right? So your actual air percentage in terms of stoichiometric conditions is equals to 100 by 5 implies 515 equals to 100 by 5 implies 5 equals to 100 by 115. So if you work this out, this will come out to be 0.869. Okay, this is your 15th question. Then moving on to question number 16. Okay, so this is 16 to 18. Information has been given. Carbon dioxide, oxygen, carbon monoxide, and nitrogen. The percentage of these has been given to us. Okay. Just give me a second. Okay, so gasoline has been given to us, right? Then the products carbon dioxide, oxygen, carbon monoxide, and nitrogen is given. But then for water, nothing has been given, right? So uh, let's say these are the moles for our given question. So these percentages, let us suppose this is not a volumetric analysis, and these are the moles that have been given, right, for different products, right? And then now what we will do, we will try to balance the equation, right? And then we will, based on this, try to solve the question. So information on question number 16 to 18. Okay. So we have yes. So we have this E8H18, right, plus O2 plus 3.76 N2. Let us suppose that the percentage is not given, but this these are the modes that have been given. Okay. So this has to be found out. This has to be found out. So this has been given. This is also given. This is also given. This is also given. And this has to be found out. Right? So four things are given and then three coefficients are not given. So first of all, what we will do, we will balance carbon dioxide. Right? So 8A equals to 9.8 plus 0.6. 8A equals to 10.4 implies A equals to 1.3. So A is your 1.3, right? Then we will balance what? Nitrogen we can balance, right? So 3.76 into 2B equals to 80.06. B equals to 80.06 divided by 2 into 3.76. So if you work this out, this will come out to be 21 point. Please check it whether this is correct or not, right? Then from here we can find out oxygen. So if we balance the oxygen terms, what we will get is that 2A equals to 2 into 9.8 plus 0.6 plus 5.34 into 2 plus C. Here A is known to us, only C we have to find out. So if we work this out, this comes out to be 11.7. Okay, this comes out to be 11.7. Please just check it whether this is correct or not. So now we have this equation. Now if we want to write with in this form. So this will come out to be this way. The coefficient of your octane was 1.3, but we are writing it 1. So all other coefficients will also change in that case. So this will come out to be okay. So now if we find out the air to fuel ratio actual, so this will be into 32, which is for oxygen, plus 3.76 into 28, which is for nitrogen. Divided by 8 plus 18, this is for your octane. So if we solve this, this will come out to be 19.7. Okay. So this is your question number 16, actual air fuel ratio. Right. Now if you solve for your equivalence ratio, so this will be so this stoichiometric is 15.05. If you balance, write the balanced equation, the stoichiometric equation, if you write, you can find out this easily. It will be air to fuel ratio will be 15.05. So this will come out to be 0.763. Okay, this is your equivalence ratio. Which means that it is a lean mixture, right? Okay, so determine the percentage of stoichiometric air used. So this will be required percentage equals to 100 by 5. So if we solve this, this will come out to be 131.06%. Okay. All right. So this was your question number 18. Now moving on to question number 19, solution. So you have been given methane and then it is being combusted using oxygen in its stoichiometric ratio. So reactants are at this reference state. We need to find out the heat of combustion. Okay. So this enthalpy of this formation for carbon dioxide, water and methane has been given, right? These somehow these negative signs have not come up, but these will be negative. So We know that this is this way. Okay, CO2 gas plus H2O in vapor state. So this way, if we have to balance this, it will be like this, right? So heat of combustion will be for first of all carbon dioxide, which is minus 298.2. Then 2 into minus of 201.1. Okay. Then for reactants, we will subtract minus of 55.4 for methane, and for oxygen it will be 0, right? For oxygen it will be 0. So if we solve this, this will come out to be minus 645 kilojoules. Okay, this is now per kg. If you want to find out, so this will be equal to 645 divided by the molecular 1 mole weight of methane, right? So we do 645 by 16 into 10 is to minus 3, which is 16 grams. And if you solve this, then this will be megajoules per kg. So this is your heat of combustion. Okay. So this was your question number 19, right? So we are now at the end of the session. So we have completed all our questions. So I'll quickly conclude this session. So this was on combustion and thermochemistry. So in the uh, topic session, we discussed 4 lectures, where we started with the fundamentals of combustion, and then we moved on to the energy balance for the combustion process, and then for the next we saw the entropy balance for these, and then how we can do the thermodynamic analysis in such scenarios. This was discussed, right? And in the last lecture, we saw topics like recuperation and regeneration, right? And things related to equilibrium. Then we moved on to conceptual questions, where we discussed 13 conceptual questions based on these topics. And later in the numericals, questions section, we discussed 7 numerical questions, right? And this way we did our session, right? And now we are at the end of session. So I thank you for watching this session, right? And I hope to see you in the next session. Next session will be on the coming Sunday. The timing for the session will be 3 to 5 p.m. Right? So till then, keep learning, happy learning, and goodbye. Thank you.